This is a walkthrough for the summer 2022 midterm exam, so let's get into it. So question 1, report the following arithmetic results or correct number of sig figs, select 1. And so I have this division here, of which I have 6 sig figs on the top and 5 sig figs on the bottom. So whatever this number is, it can only have 5 significant figures. Here on top I have 1, 2, 3, 4, 5, 6 sig figs, and then down the bottom I've got to look at the math. So this is going to the third decimal place. This goes past the third decimal place, so I can only keep to 3 decimal places. So I can only keep this, which means down the bottom only has 3 sig figs. So when I do the division here, I can only keep 3 sig figs. And those are going to be subtracted from each other. So that's right here. And so whatever those numbers are, so we're going to have to look. So what is this number? Can it only have 3 sig figs? So here's that number. It can only have 3 sig figs. So in the ones place. So when we add these together, right? This can have 3 sig figs. It'll be in the ones place. That can have 5 sig figs. And that will be up top, so that'll be to the 0.1 place. So when I add these two together, I can only keep to the ones place. So right there. And then I'm going to, or when I minus those, and now I'm going to add a logarithm to it, and that thing has 1, 2, 3, 4, 5, 6, 7, 8 sig figs. So the logarithm will have 1, 2, 3, 4, 5, 6, 7, 8 sig figs, or 8 decimal places. When I add those together, this ones place still wins. So the answer will be B. Report the following arithmetic result for the correct number of sig figs. So here, up top, I have 1, 2, 3, 4, 5, 6 sig figs up top. And down the bottom, it looks like I have 2, but when I add them together, you really have 3 sig figs. So when we do this math here, all together, right here, we can keep 3 sig figs, so to the third decimal place. So when I add it to 111, which has 4 decimal places, I still can only keep to the third decimal place. When I add to logarithm, this log has 1, 2, 3, 4, 5 sig figs. So 1, 2, 3, 4, 5 sig figs. So still, my problem is I can only keep to the third decimal place because of this. Right, fourth decimal place because of this, and of course well beyond with this. So once again, I'm limited to that third decimal place. So the answer is D. For the rule below, how many significant figures should be reported for the measurement of the bar? Well, let's measure the bar. The bar is going to be 54.797. I'm going to say it's 89. And then this edge of the bar will be 54.797. And I'm going to call that 1, 2. So 9 minus 2 is 7. 8 minus 1 is 7. 1, 2, 3 decimal. So I have 2 sig figs. So the answer is 2 sig figs. Select the definition of a significant figure. Well, all the certain digits that follow the decimal place, no, that is wrong. All the certain digits plus the first uncertain digit, which is the definition we've used in class. All the certain digits that precede the decimal place, absolutely wrong. All the certain digits plus 2 uncertain digits, no. And all the certain digits and no uncertain digits, that would not be right. So the answer for 4 is B. Report the following arithmetic result with the correct number of sig figs. Select 1. So the key for this is always to put it in terms of the answer. So the first one is 9.533. Oops. I need to turn this to 10 to the minus 11. So this is minus 13, right? So it's smaller than minus 11. So 12, 11 would be like this. So 0.09533 times 10 to the minus 11th power. This is 12, right? So it's 1 smaller. So that would be 0.339 times 10 to the 11th. This is 10 to the 14th. So 1, right? So that's 13, 12, 11. So 0.0076 times 10 to the 11th. And of course the last one is just 10 to the 11th, so 0.26423. And as you can see, the highest uncertainty is in this third decimal place. So when we add these together, the answer will be E, that third decimal place. A student calculates the average and standard deviation for the pressure known gas. Dow for the gas meter shown. How should this be represented? Well, rule 1, right? This must be reported with 1 sig fig unless it begins with a 1 or 2. So plus or minus 0.00025. Rule 2, this must match 2.33254. And then rule 3, are we doing better than the instrument? So what's the instrument error on this? So I can already see what the instrument error is and the precision of it, but let's try a little test. I'm just going to put a dot here. Let's measure what that actual number would be. So that would be 12.4, and then it's greater than 5, but not 6, and then maybe half of that again. So that's where we get all the certain digits plus the first uncertain digit. So the instrument error, of course, would be plus or minus 0.001. So the question is, what's bigger, this or that? And of course this is, so we can't use this, right? We'd have to use the 12.333, which is A. A student calculates the average and standard deviation for a pH of an unknown acid as this, plus or minus that. The pH meter shows 2 decimal places. How should the result be presented? So you've calculated an average pH and a standard deviation. So once again, rule 1, we'll apply to this. So rule 1 is 0.029, because right, we can only keep 1 sig fig, right? Unless it begins with a 1 or 2, so I have 2. But that 7 is going to have it round. So that 7 is going to take it to 3.0. And once we have that 3.0, we are no longer 2, so we have to keep it as 0.03. Now, also, rule 2, 1.54, and then rule 3, what's the instrument error? So it's 2 decimal places, so plus or minus 0.01. 0.03 is bigger, so the answer is B. Number 8, a student calculates the average and standard deviation for a pH meter as this. The pH meter shows 3 decimal places. How should the result be presented? Well, rule 1, the error can only be reported with 1 sig fig unless it begins with a 1 or 2. This is not the case. 0.00, and that 7 will round to an 8. Rule 2, 9.526. Rule 3, the instrument error is 0.001. So which one is bigger? Right, of course the 0.008 is bigger. And so the answer is going to be B. Student measures the pH of an unknown acid 3 times and obtains an average of 7.52. 8232 and a standard deviation of this. The pH meter shown below. How should the result be presented? Well, rule 1, plus or minus 0.25 because it rounds. Rule 2, 7.53, and rule 3, this is plus or minus 0.1. So therefore 1 is smaller. However, we can't report it as such, right? Cannot be reported as such because the instrument, right, says we can only keep that 1 decimal place, so I can't keep this 5. But I also can't toss it out. It's too much error, so that has to round up. So this is when rule 1 and 3 clash, right? We have that whole slide. So this is plus or minus 0.3 and 7.5. So the answer for that is C. An acid has a Ka value of this. The corresponding pKa value on your calculator is that. Report this pKa with the correct number of sig figs. Okay, well our Ka has 4 sig figs, which means our answer must have 4 sig figs. But remember, the pKa is a logarithm, and all logarithm sig figs are to the right of the decimal place. So I can keep 1, 2, 3, 4 sig figs. So 3.0499, but that 7's going to round it up. We'll get 500. So the answer for that is C. The pKa of an acid is reported as 11.034. The corresponding Ka value is shown as this. Report this concentration with the correct number of sig figs. Well, remember, pKa, this is a logarithm. So once again, the sig figs are only to the right of the decimal place. So this only has 3 sig figs. So this number can only be reported with 3 sig figs. And that 6 will have it round up to a 5. And so the answer is E. A student measures the mass of a precipitate for 6 trials using the balance below. And calculates this in a sample standard deviation of that. How should the student represent the results? Well, rule 1, plus or minus 0.000. That 7 will have the 6, right? Can only keep 1, so that's 7. Rule 2, 32.734, and that 3 will round up because of the 5, so it's a 4. And then rule 3, are we doing better than the instrument? Well, the instrument is 0.001, right? You can see that here. It's that last decimal place. So the 0.001 is better than or bigger than 0.0007. So we can't use this. We have to use that. Right? So the answer is B. You create 3 solutions to test your new Alzheimer's drug. You weigh the drug on a balance that has precision to the 4th decimal place and use it. See, there's the 4th decimal place. You use a burette that has the precision to the 2nd decimal place, and this is in liters, right? So that would be milliliters, and that would be the 2 decimal places. So that's correct. Good. You calculate the concentration for each of the solutions using a calculator. Here's the first calculation of the first trial. The average concentration sample standard deviation for these solutions show up as this. How should your result be reported? Well, rule 1 is report the error with 1 significant figure, unless it begins with a 1 or a 2. It begins with a 2, so we got to keep 2. So 0. Let's see, 1, 2, 3, 4, 5, 6 zeros. 2, 3, 4, 5, 6 zeros. 2, 3. Then this must be reported with the same precision as your error. So that was what? 1, 2, 3, 4, 5, 6, 8 decimal places. So 0.00349771. And then rule 3, what's the instrument error? Are we doing better than instrument error? Well, let's find out. I have 4 sig figs here. I have 4 sig figs here. I have 1, 2, 3, 4, 5 sig figs there. So when I do all this math, I can only keep 4 sig figs. So I can only keep 4 sig figs. So that's 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 is my instrument error. So my instrument error is way larger than my average. So I cannot keep the average. I can't use this, right? I'm going to have to use the 0.003498. So the answer is D. Same question, except for a new trial and a new average and standard deviation. Once again, the solution to this is the same. Once again, 4 decimal places, and once again, to 2 decimal places for the burette. So, rule 1, I report my error with 1 significant figure, unless it begins with a 1 or a 2. I report my error to that, and then I compete it with the instrument error. So I have 1, 2, 3, 4, 5, 6 sig figs. I have 1, 2, 3, 4, 5, 6 sig figs, and here I have 3 sig figs. So here, once again, I can only have 3 sig figs. So that means my instrument error is in this place, so it's plus or minus 0.1. So plus or minus 0.1 is larger than 0.06, so I cannot keep this. So it's 32.7. -0.2. You create 3 solutions to test your new Alzheimer's. So same question once again. New trial, new average of standard deviation. Same solution though. Rule 1, you report the error with 1 sig fig unless it begins with a 1 or a 2. Report the error, report the value to the, and then to the same magnitude as the error. And then 3, what's my error in my calculation? Well, I have 5 sig figs, I have 3 sig figs, and I have 4 sig figs. So that means I can only keep 3 sig figs, which means my instrument error here is plus or minus 0.001, 0.001, which is smaller. This is bigger. So that means you stick with the larger one, right? Which means your answer is going to be C. You buy 2 identical thermometers and use them to measure the equilibrium temperature of water. The temperature is measured 50 times and the average of standard deviation are calculated. Thermometer A is 10, plus or minus 2, and thermometer B is 30, plus or minus 6. The temperature is known to be exactly 15 degrees C. Select 1. Okay, well, we're looking at either is it more precise or accurate or none. Okay, so let's look at precision first. So let's calculate the precision of A. The precision of A is simply 2 standard deviation over the average, right? If you remember, it's simply S over X bar. So 2 over 10. And then B is the same thing. It's going to be, which equals 1 over 5. And B is going to equal 6 over 30, which equals 1 over 5. So this means, right, because their RSD here is the same, their precision is equal, right? So it can't be more precise and it can't be less precise. They're exactly precise. Okay, well then let's look at their accuracy. So we're going to look at the percent error, right? And so for A, here's our theoretical value. It's going to be the absolute value of 10 minus 15 divided by 15. And for B, right, it's going to be 30 minus 15. Oops, that's not 30. Over 15. So this will be 5 over 15. Okay, and this will be 15 over 15. Okay, so we can clearly see that this is equal to 1, right? And this is going to be 1/3. So this is more precise, right? I mean more accurate, right? So the answer is A. Thermometer A is more accurate. There we go. Select the false statement. Random errors shift results in one direction. Well, we know that's false because only systematic errors shift in one direction. Random shift randomly in both, right? Systematic errors in theory can be identified. True, right? Just like experiment 4 or with a standard, right? You can see if the measuring tape has been too short. Random errors always have a Gaussian distribution. Yes, we use statistics to unravel random error. RSD allows comparison of the precision between instruments. Absolutely true. That's what we just did in the problem before this. The standard deviation reflects the probability of repeating a measurement. Yes, right. The standard deviation tells you if you're plus or minus 1 standard deviation, you have a 68% chance of repeating that. So 17, the answer is A. After 99 trials, the average mass delivered from a pipette is 50 with a standard deviation of 2. If you perform a 100 trial, what is the probability the mass will be between 44 and 52? Select 1. Okay, so let's do our Gaussian. Here's 50. So 1 standard deviation to the right is 52. So that's 1 sigma to the right. And then down 1 is going to be 48. Down 2 right, will be 46. And down 3 is going to be 44. Okay, so there's two ways to solve this. This one's probably the easiest. So let's just deal with the right-hand side first, right? Well, this is 3 standard deviations away. So 1 standard deviation away here, right? If you're inside 1 standard deviation, right, you have a 68% chance of being in that area. But I only have half of that area. So I really have 68 over 1/2, right? So right here for this area, it's 34% chance. Okay, what about 3 standard deviations? Well, if this is 68, that's 95. That's 99.7 of being in plus or minus, 3 standard deviations. But once again, I only have half of that. Okay? I only have half of that. So it's 99.7 divided by 2. So it's much easier to take this 0.3 that's left over and saying, well, half of that is 0.15, right? And saying, well, half of 100 is 50%, right? 50, and then minusing 0.15 from that, right? So that would be 49.85. So this is 49.85, right? So 49.85 plus 34. Now, if you can see the math already, there's no decimal place here. You can already see there's only 1.85. But if you add these together, you can see it becomes 83.85. So as long as you can see that this goes to an 85 just by doing this math here, you can get the answer. You also can rule out a lot. It's not going to be 99.7, right? Because that would be 3 standard deviations. So that's really at least one thing you can rule out. These two are relatively close, so this is a little more challenging. But, I mean, I'm literally asking you to do 3rd grade division here. So, yeah. So, select a true statement about RSD. More than one of the other statements is true. Well, let's look at the other statements first. The sample RSD equals the population RSD when the sample average equals the population average. This is going to be false, right? There's many times that the sample average has the ability to equal the population average. And it just so happens maybe on n equals 1, you get the number right the first time, or n equals 3 and you get it right. This has nothing to do with it, right? This was only going to occur when n approaches n, and not when x bar approaches mu, right? That's the wrong thinking. So C, the sample RSD approaches the population RSD as the sample size approaches the population size. Well, we never really talked about what RSD does, right? When we talked about when n approaches big N, right? We talked about x bar approaching mu, and we talked about s approaching sigma. But we never talked about RSD. Well, what is RSD? Well, RSD just happens to be s over x bar, right? And if s approaches sigma, and if x bar approaches mu, then yes, this is the population RSD, and this is your sample RSD. So this is absolutely true, right? Absolutely true, because we know these two components that we've talked about here would do this. So let's see, D. The sample RSD approaches the percent error when the sample, RSD accuracy and error have nothing to do with each other, and none of the statements are correct is incorrect. So the answer is C. How should you report an average and its corresponding standard deviation? Select 1. The average and standard deviation should have the same number of significant figures. Well, that doesn't make sense because we report the error with 1 sig fig and the answer can have a lot more. So, absolutely wrong. The average should be reported with 1 sig fig unless it begins with a 1 or 2. No, not the average, the error. So that's false as well. The average should be reported at the same decimal place or precision as the standard deviation. Yes, this is rule 2, right? Should report it to the same precision. The average and standard deviation should have the same number of significant figures. Once again, I've said that up top. It's a previous answer, and that's absolutely not. And no, once again, this won't apply because we do have a true one. So the answer for 20 is C. Select a true statement. The percent RSD provides information on the relative accuracy of one measurement to another. So RSD provides information not on accuracy, but on precision, right? So that will be false. Repetition of a measurement will make random error smaller. It doesn't make it smaller. You just know it better, right? It never makes it smaller. It'll never go. That means if I do a ton of measurements, it'll disappear. No, random error will always be there. It's part of nature. And if you don't believe me, go look at the Heisenberg uncertainty principle. C, random error is known better with repeated measurements. Yes, right? Because the error of the error goes down as n gets up. Remember, it goes 1 over square root of, what is it, 2s or something like that? 2s minus 1? 2s minus 1 or something like that? Random error can be compared by calculating percent error. No, not random error, right? Systematic error is compared by that. And then systematic errors reflect statistical fluctuations within measurement. No, random errors reflect that, so false. So the answer is C. 22. You have a balance that is not calibrated and weighs that reads weights too low. Use this balance to measure the mass of a beaker multiple times. What happens if you increase the number of measurements with this miscalibrated balance? Right? So the sample mean approaches the population mean, right? This is true, right? You just have a sample and population, right? So it just will approach no matter what, even if it's off. Remember, we talked about this with Gal-Godet, right? With that whole being miscalibrated on a balance. That even though you get an average, right, if you know what the offset is, you still have good data, and that the sample mean approaches the population mean. Even if it's miscalibrated, it goes to the incorrect balance, but it will still approach. So let's see, the sample mean B. Sample mean approaches the true value of the mass on the beaker. Well, the sample mean will never approach the true mass because it's out of calibration. So false. The population mean approaches the true value of the mass of the beaker. Once again, out of calibration, so false. The sample standard deviation becomes small and approaches 0. Right? No, that'll never happen. The sample standard deviation becomes large and approaches infinity. No, those are just 2 fillers. So really we had 3. Do you understand it's out of calibration? And then once it's out of calibration, right, we talked about this with Gal-Godet. Your data is still good. The sample mean still approaches the population mean. And you can either adjust it back with the correction factor for the offset, or you can leave it as is, but it will still approach the correct value, right? Or approach the correct offset value. Right? So this goes back to that Gal-Godet, how much do I weigh slide set. What is the correct reading for the burette on the right? Select one. Well, it's bigger than 33.6, but less than 33.7. So it's 33.6. And then I'm going to go, that's 5, that's a 6, that's a 7. It's not as big as 6, and it's less than 7. So 6, and then the last number I'll guess is another 6. So basically, it's 3 decimal places. Okay. And it'll begin with 33.6. Right? It has to begin with 33.6, and it has to have decimal places. So 33.7 is right out. And then there's only one with 3 decimal places. So it is going to be C. You've decided to join the military. To do so, you must go through a very complex physical. For part of the physical, a technician needs to weigh you. You step on the balance, and it reads that you're 180 kilograms. Wow. You find this odd because you weighed 112 kilograms at home and 112 kilograms at the doctor's office the other day. You step off the balance and think about this. So, right, what we're showing is we have a consistent mass and a mass that's off. We're not showing that a number is bouncing to the left or the right, right? We're not showing random error. We're showing a large offset. So what is this most likely due to, right? If we can show that these balances, right, are plus or minus, right, to the 1 kilogram place, or maybe even the 10 kilogram place, we're not showing a lot of variation, right? So this is most likely not a random error, right? So it's not a random error, right? It's not a precision, right? Really, what is wrong is this is miscalibrated, right? And what are miscalibrations? Miscalibrations are systematic errors. And that's really what we're looking for here, right? Right. Random error, precision. Random error, precision. RSD, precision. Weight increase, precision. All of these answers are arguing precision. There's only one systematic error answer there, okay? So when you see this, right, especially if you have a balance, if all the numbers are in the same neighborhood and one is way off, right, this is more likely a systematic error because it will always read people heavier, right? No matter how much these people weigh, it'll always read them heavier than they really are. This is a challenging one. It's designed to make you hopefully see these in the real world. Yeah. Great job on the test, though. Very impressed. I'm very proud. You all did a really good job.